Hey everyone, in this video we're going to discuss the implementation of Cascade, Ratio, and feed-forward control to improve the performance of feedback control loops. We're going to start with this example shown here where we have a continuous stirred tank thermal mixer that has cascade control on the flow to the feed inlet to the process. Okay, so first what I want you to do is describe how the system would operate in feedback control only. So pause the video, draw this out, and then we'll discuss it in just a second. Okay, so for this process, the primary control objective is the temperature of the product stream coming out. So we want to measure the product stream. We'll have the primary controller is going to be on the temperature, is going to be a temperature controller to control for this temperature. And there's going to be a user specified set point. So in feedback control only, this controller is going to have the valve open or close, okay? The other loop over here, or the other components over here would not be part of a feedback control loop. So the way this would work is that when the temperature of this process changed based on any type of disturbance affecting the process, the controller is going to tell the valve to open or close to get the temperature back to the set point. All right, so the next thing we can do is list the disturbances that can affect the temperature in this process. So pause the video and list the disturbances that can affect the product temperature. All right, for this type of system, there's a variety of disturbances that are going to affect this temperature. We can think about the temperature so the temperature of the feed stream 1 entering the process. If this temperature changes, it's going to affect the temperature of the process. Temperature of stream 2. Okay, so the flow of feed 1 is our manipulated variable, so we won't count this as a disturbance, but the flow of feed 2 could change, and if the flow of feed 2 changes, this is going to affect the temperature. Right? If the flow of feed 2 changes, it's probably going to change the level. So on this system, there would likely be an independent control loop. So this could have an independent control loop where we have level control. And the level controller on this independent control loop could be controlled, for example, by changing the flow out of the product stream. All right, so these two loops will work independently of each other. All right, other disturbances. Let's think about what could affect this. The temperature of this stream coming out. We have the feed temperature and the temperature of this stream. Okay, but the valve, there's a valve right here, so we know that the flow that goes through this valve is a function of the pressure difference. It's likely that the pressure on this side of the valve does not change, but the upstream pressure to the process could possibly change, and that would affect the flow through this valve without anything else otherwise changing. So another disturbance to this process could be the pressure upstream. Okay, if we know that the pressure upstream is going to be the main disturbance for this process, we want to minimize the effect of this change in pressure by incorporating an inner loop or a cascade loop so that we can make sure that this flow does not change, which would ultimately affect the process. So we want to account for changes in this upstream pressure by controlling the flow through this valve. And that would require us to add a cascade loop around this manipulated variable. Because remember, cascade schemes are most effective when they're incorporated around the manipulated variable. Okay, so in this case, we're going to incorporate, we're going to measure the flow through the system. We have a control valve on the flow. Okay, so this is going to be our cascade loop. So the flow goes to the controller, and then this is going to change the flow valve. All right, so the way Cascade works is that our primary control objective, this temperature set point, so this is the main thing we care about. Okay, this controller is going to provide the remote set point to our inner control valve, or to our inner controller. So this is going to be a flow rather than a valve position. The controller, or the The controller is going to take the measurement of the flow, compare that to the flow set point that's set by the primary control loop, and change the valve. Okay, when the system operates this way, any sort of changes in the upstream pressure that would cause this valve to change are going to be corrected for before this flow significantly changes and affects the process. And this is going to make changes in the temperature less severe. Okay, so let's take a second now and let's think about or describe how the system responds when the upstream pressure increases by, let's just say, 10%. So increase in upstream pressure. Okay, so what happens first? An increase in upstream pressure is going to cause an increase in flow 1. Okay, when flow 1 increases, the flow valve or the flow controller is going to measure that increase, and it's going to request that this valve closes. So the increase in flow 1, we're going to close the valve to decrease the flow, and this is going to bring flow 1 back down. Okay, so the last thing we want to do with this example before we move on to some of the other examples is to draw the block diagram of this cascade loop. And we're going to do that on the next slide. Okay, so as before, we still have a specified value. So on the block diagram, we have our specified value in the control variable. So T specified. Okay, so again, so just like before, the specified value is going to be compared to the sensed value. Okay, so somewhere on here, on this block diagram, we have our temperature sensor. Okay, and the temperature sensor, and I'm just going to draw this line over here, is going to measure the temperature of the process. So the temperature of the process is going to be our primary control variable. Okay, so what we have in this cascade system is now where we have the specifieds compared to the temperature, or compared to the sensed temperature, and this value, this will be our error as previously. This is going to go to our temperature controller. Okay, the temperature controller is going to provide the remote set point to our inner controller, right? And so the inner controller is going to compare this remote set point to the sense value. So the sense value in this case is going to be a flow. So we'll call this F. So the flow entering the system, this would be F1. I'm just going to call it S for this system right here. This would also be measured by the flow sensor. And so over here, I'm just going to write, we have a flow through the actuator. So this flow through the actuator, it's going to be measured. And this is going to be compared to the remote set point. Okay, so now the remote set point, again, this is going to have an error. We'll call this E2. And this error is going to go to, I'm running out of a little space here, but this is going to go to a flow controller. And then the flow controller is going to affect the actuator. So this box right here would be our actuator. And coming out of the actuator is going to be the flow. So between the flow controller is going to set a valve position, which valve position to the actuator is going to affect the flow, and the flow is going to affect our process. All right, so this right here shows an example. This is the example of the block diagram for the Cascade scheme. So these are things that you should be able to do for various systems that are set up with Cascade. All right, let's go through and do a few more examples. Okay, we'll start. This next example we'll do is level in the tank. So we're gonna do two examples for level in the tank. One we'll do ratio, one we'll do cascade. So ratio control that we said, this is done when the feed to a process is proportional to the manipulative variable. So the manipulative variable here is the flow out. So if the feed to the process is our disturbance, so if F in is the disturbance, we can do ratio control to minimize the effect of the flow in on the level of the process. Now, how might we incorporate cascade control? So cascade, again, this should be incorporated around the manipulative variable. So one of the disturbances that would change the flow through the manipulative variable without anything else changing to the process could be the pressure downstream. And we'll just call that P downstream. So if the pressure downstream is the disturbance, we can minimize the effect of that disturbance by incorporating cascade. So let's do a cascade loop on this process. All right, in feedback control only, again, we're measuring the level. The controller is going to compare this level to the set point, and it's going to tell the valve to open or close. Okay, so for cascade, the primary controller, remember the main thing is that the primary controller is going to provide a remote set point to a secondary controller. Okay, a secondary controller is going to take the measurement of some value. So the secondary controller is going to take some measurement, and here I can just write measurement. This is going to be some type of controller, and the secondary controller is going to change the valve. Okay, if the pressure of the downstream changes, is going to affect the flow out. Okay, so we want to measure the flow out. So the measurement of the flow out is going to go to the flow controller because that's what we're measuring, and then we're going to change the valve position. Okay, so we can put this flow sensor on either side of the valve. It doesn't necessarily matter for the sake of this example. So now if we look at how this process works, is we have our the primary control objective, or the outer loop, is the level control. That's providing the remote set point to the inner loop, the flow controller. The flow controller is taking the measurement of the disturbance, which is the flow out, which is affected by the pressure downstream, and is changing the valve position before the process is affected. So as this pressure downstream changes, the flow changes, and this inner loop right here is going to account for changes in the flow due to changes in the pressure of the downstream and keep the process closer to the target specified level. Okay, so they're cascade to minimize the effect of the downstream pressure or changes in the flow out. Okay, this time we'll look at ratio control, and we said we'd have ratio control when the primary disturbance is the flow in. So if we have ratio control, again, same thing, we measure the disturbance. The disturbance is going to go to the ratio controller. Okay, the ratio controller is going to take a remote set point from the primary control loop. Okay, so the primary control loop is the level controller. The level controller is going to provide a remote set point, which is a ratio, to the ratio controller, and the ratio controller is going to change the valve position to this valve. Now note that what we could also do in this case is we could set this loop up as cascade as well to account for changes in the flow out to the system. Okay? Important thing to remember about ratio control is that our primary control objective, we have a main control objective, the control variable. This controller provides the remote set point to the ratio controller. Okay, so as you set up a ratio control, the ratio control is going to take the measurement of the disturbance, which is a feed flow to the process. It's going to take a remote set point that comes from the primary control objective, and it's going to set the valve position, or it could provide a remote set point to a for example, inner flow control loop. Now let's look at an exothermic reactor that uses cooling water to cool the reactor contents and keep the reactor system at a specified temperature. So the primary control system in this case, or the primary control variable, is the temperature. So the temperature of the product is our CV. This is our main control loop. We're going to measure the temperature, compare it to a specified value, and this is going to open or close the valve of the cooling water to keep the temperature where it wants to be, or where we want it to be. Okay, this process can have a variety of disturbances, so we're going to do two examples. We're going to look at one where we implement Cascade and one where we implement ratio control. So some of the disturbances that can affect the process are the feed flow, so the feed flow, the feed temp, but also the cooling water temp can affect the process as well. Okay, so we said that Cascade can be used when the disturbances are around the manipulated variable. So what I want you to do for this example is draw a Cascade scheme that accounts for a disturbance associated with the cooling water. So for example, the cooling water temperature. So pause the video, do that, and then we'll go through it. Okay, so if the temperature of the cooling water changes, we know that that temperature of the cooling water is going to first affect the temperature of the cooling water in the jacket, and ultimately it's the temperature of the cooling water in the jacket that's going to affect the temperature of the process. So if we can account for changes in the temperature of the cooling water by measuring the temperature of the cooling water jacket, again, we want to measure the temperature in the jacket because this is the component that affects our control variable, right? So that's the important part of Cascade. We measure the component that affects our control variable. So for this inner control loop, or this Cascade control loop, we measure the temperature. We have a temperature controller, and so I'll call this TC, so temperature of the Cascade controller. So we measure the temperature, it goes to the temperature controller, and the inner control loop, or the Cascade loop, is what's going to change the control valve. So the primary control loop is going to provide the remote set point for the inner loop, and that's going to change the valve. Okay, so now if we think about if this cooling water temperature changes, it's going to first change the temperature in the cooling water, and then this inner controller can change the flow of the cooling water to get the temperature where we need it to be so that the process doesn't change by too much. And then the primary control loop can, again, change the remote set point so that we get the temperature where we need it to be. So in addition to disturbances located around the cooling water, we can also have disturbances that are associated with the feed. So we can have a change in feed flow, or a change in the temperature of the feed that's entering the system. So if either one of these changes, we can account for these by incorporating another type of feed forward control strategy. All right, we said before that if the feed flow rate is the primary disturbance, then we can use a ratio control. Okay, for this case, the flow of the feed isn't really proportional to the flow of cooling water based on our energy balance for the system. But we know that if the temperature of the feed increases or decreases, we'll need to change the amount of coolant to the system. So we can account for maybe changes in the feed temperature using a feed forward scheme. So we would do this, again, we can't cascade, it's not around the manipulated variable, it's not a feed flow, so we can't use ratio control. So what we need to do is some sort of just general feed forward. Okay, so in this case, we would measure the disturbance, put a temperature here, and then we have a feed forward controller. Okay, and then the feed forward controller is going to change the flow or change the manipulated variable. Now remember, feed forward control by itself isn't going to be effective, so we have to combine feed forward with feedback control. So in our feedback control loop, which is shown here, measurement of the product temperature, and the feedback control loop is going to ask for a change to the manipulated variable to keep this at the target value. So for our feed forward system, we would just have combine the signal from the feedback in the feed forward loop. So if we think about now how this works, when the temperature of the feed doesn't change, the feedback control loop is going to open or close the valve. So this signal will be 0 and all of the action will come from the primary control loop. If the primary control loop is at its specified value, but a temperature of the feed increases, we can accommodate for changes in the increased temperature before the processes change. We know an increase in temperature will eventually affect this process, but if this temperature increases, immediately, the feed forward controller will have this valve open to start cooling the system more before the product temperature changes too much. All right, let's look at an example here where we have a steam drum and we're boiling water to provide steam to users. So as steam is pulled off, makeup water is delivered to the drum to keep the level at the target value. So when this system operates in feedback mode, the user enters a specified level, the level is compared to the measurement of the level, and the level controller will open or close the makeup water valve to keep the level at a target set point. But we know that for these cases, the amount of steam that's being used should be identical to the amount of makeup water that's sent in based on the mass balance. So we could design a system that instead of using the feedback control, so let's kind of scratch off this feedback control, we could run this system entirely using feed forward control. So draw a feed forward control only on this process. Pause the video and then come back. All right, so for feed forward control, we want to first measure the disturbance. So we're going to measure the flow of steam. The flow of steam would be sent to a feed forward controller. So a feed forward controller does not have any user specified input. That's only feedback. So feed forward controller now is going to open or close the valve to keep based on the measurement of the flow of the steam. All right, if we want to incorporate this now with feedback and feed forward control, we have our primary control loop, our feedback control loop shown here. So we have a specified level, we take a measurement of the level, and this changes the valve. Okay, so feedback or feed forward, we do the same thing as we did over on the other side. We have our feed forward controller, and both of these signals would be combined together to change the control to the system. Okay, so what I want you to do now is draw a block diagram for the for the feed forward control scheme. So feed forward only for this process. Okay, so I'm going to go ahead and start here. We know that there's two things that are going to affect the level. Okay, so this level is going to be changed based on the disturbance, which is the flow of feed coming out, and it's going to be changed based on the makeup water coming in. So I'm going to have two signals that are going to be combined together that can affect the level. Okay, so one of those signals is going to be the actual disturbance or the flow of steam coming out. So our disturbance in this case is going to be flow of steam. So we have the flow of steam. It's going to affect our process somehow. So this is the process. This right here, we can call this box the disturbance process. And so the disturbance process is going to affect the level. So the way feed forward works is we take the disturbance and we measure the disturbance. So the disturbance has to be sensed. So we have a disturbance sensor. So coming out of the disturbance sensor is going to be the flow of steam sensed. We'll call that FSS. And this sense value is going to be sent to the feed forward controller. So the feed forward controller is going to have a signal. So the signal, call this controller signal feed forward. So this feed forward controller is going to change the actuator. Okay, the actuator is going to affect the process. So this actuator is going to be the flow of cooling water. And the flow of cooling water is going to affect our main process, which is the level. So this right here would show us the block diagram of a feed forward only controller. Now what I want you to think about is draw a block diagram of a combined feedback feed forward controller. You might see this coming up soon. Okay, let's now consider an example of a heat exchanger where we use steam to heat a process fluid. And if we look at the system, so our primary control objective for a heat exchanger is the temperature of the process stream coming out of the heat exchanger. So in feedback only mode, we would specify the temperature of the product stream, measure the temperature of the product stream, and then the controller is going to change the valve position on the steam to keep the temperature where we want it to be. So again, there's a variety of disturbances that can affect this process, so we're going to look at a couple of them. Okay, so one disturbance could be the pressure of the steam. If the pressure of the steam changes, it's going to change the flow of steam through the process. So we can account for that, possibly using a feed forward strategy. We can also have the feed flow. So the feed flow can change. We also could have the feed temperature can change, which is going to all affect the process. All right, so first, let's draw a feed forward control strategy, cascade ratio, or general feed forward, to account for changes in the pressure of the steam. So go ahead and do that. Okay, so if the pressure of the steam were to be our disturbance, that would affect the manipulative variable. So we can account for changes in steam pressure by incorporating a cascade loop. So we can do this by measuring the temperature of the steam. So we have a pressure sensor. We have a pressure controller. So the pressure is going to be measured. It's going to go to the pressure controller. And the pressure controller is going to change the valve position on the steam. I drew this over the feedback control loop because we know that the primary control loop is going to send a remote set point to the inner control loop. So the primary control loop provides a remote set point to the inner controller. We measure the disturbance, which is the pressure of the steam, change the valve accordingly. So this is going to account for changes in steam pressure. I want to note on this system right here, this inner cascade loop, I used pressure control pressure sensors. You can also do the same thing using flow. It would have the same effect. All right, what if the feed flow rate were to change, or the feed temperature? If the feed flow were to change, we said that ratio control can be used to account for changes in feed flow rates when they're proportional to the manipulative variable. Again, in this case, the feed flow is not quite proportional to the flow of steam into the system, or the pressure of the steam. So that would be hard to incorporate using feedback or using a ratio type controller. Instead, let's draw a design scheme to account for changes in feed temperature. So the main disturbance, if our main disturbance is feed temp, in this case, if the feed temperature is the main disturbance, we measure the disturbance. The disturbance would go to our feed forward controller, and based on the temperature of the feed, we can determine how much heating needs to be done to the system. So the feed forward would go and be combined with the feedback. Again, we have our T specified. Change the valve position on the steam. So in this case, if the temperature coming in changes, we can have the valve or the temperature coming in, let's say, decreases. We can ask for a higher amount of steam to the valve before this system actually changes to prevent the temperature of this process from changing. Also note that, like before, we can incorporate the same type of cascade scheme inside this feed forward stream as well. Okay, so again, when you're incorporating multiple types of feed forward streams like cascade, ratio, feed forward, they can be implemented together in different ways, and you just need to be careful that you're setting them up properly. And we'll do a few more examples on this. Let's look at a process that uses a furnace to heat a process fluid. Okay, in this case, because we're heating a process fluid, the thing that we care about is the temperature of the process fluid coming out of the furnace. So because we care about that, we need to measure it. So this should be TT, not TC. So we measure the temperature. The temperature is compared to a specified value. So this is our primary control variable. And then in feedback only control, our primary controller would open or close the amount of fuel that's being sent to the furnace to keep our process fluid at the desired temperature. Okay, so there could be, again, a variety of types of disturbances that can affect this process. We could have the flow of process fluid, we could have the temperature of the process fluid coming in, we could have maybe the pressure, the flow of the liquid fuel, possibly the composition of the fuel, etc. Okay, so what I want you to do is I want you to draw a feed-forward control strategy to account for changes in the process fluid feed flow rate. So the disturbance is the feed flow of the process fluid. Okay, so in this case, because our disturbance is a feed flow to the process, the flow rate of the liquid fuel that's being used to heat should be proportional to the feed of the process fluid, or the feed rate of the process fluid. So we would measure the disturbance. Okay, the measured disturbance is going to go to our ratio controller because the disturbance is a feed. The primary control loop is going to provide our remote set point, and then the controller is going to change the valve position. So this is how we can incorporate a ratio controller to account for changes in the process fluid feed flow rate. Now, if we knew we had a disturbance associated with the flow of the liquid feed, we could incorporate inside here a cascade scheme. So think about how you would incorporate a cascade scheme to account for changes in the liquid fuel feed to the process. Okay, let's do an example. Let's do a problem from the textbook. So in this problem, we have a continuous stirred tank reactor that's equipped with a vent stream. So we have a vent on this reactor so that the light impurities don't accumulate in the vapor space above the reaction mixture. So what we want to do is we want to add a ratio controller that adjusts the ratio of the flow rate of the vent stream to the reactor feed flow rate to maintain the composition of the light impurities in the reactor space. Okay, so our primary control objective. So let me stop here. I want you to work on this for a second, and then we will work through it. Okay, so our primary control objective is we want to maintain the composition of the light key, of the light component. So because we're trying to maintain the composition of the light component, we can draw on there our primary controller. So our primary control loop is the composition of the components up here. And if this were operating in feedback only mode, we would have the composition controller open or close the vent to keep this at the right composition. But what we're told is that we want to add a ratio controller to adjust the ratio of the flow rate of the vent stream to the reactor feed flow rate to maintain the composition. Okay, so this tells us what we want to do, so we just have to set up the ratio controller accordingly. So we're ratioing it to the feed flow rate to the process. So again, here we measure, so the feed flow to the process, we would measure that. Okay, this measurement is going to go to our ratio controller, X. Right, and so now The primary control loop is going to set the ratio to the ratio controller, and then the ratio controller is going to change the valve. So this is how we'd integrate ratio control into this CSTR. So now in this case, if we want to talk about what would happen if this feed to the process changed, so immediately as this feed increased, we could increase the vent, open the vent to keep the composition where we want it to be. Okay, let's look at this problem. This is a little bit more tricky. So this is asking to draw a schematic for the rectifying section of the distillation column, the top, in which a composition controller of the overhead product, so composition of the overhead product, so we're trying to, this is our control variable, is cascaded to the tray temperature controller. Okay, so composition of the overhead product, so we're measuring the composition, so we need a composition controller, and this composition controller needs a set point. So we take measurement of the composition. Okay, it says this is cascaded to a tray temperature controller. So here we have a tray, we're measuring the tray temperature. And so because we're measuring the tray temperature, there should be a tray temperature controller. So the terminology, when it says the composition controller of the overhead product is cascaded to, so is cascaded to, this terminology we can think about interpreting this as sending, let's see if I can write it on here, sending a remote set point. So is cascaded to means sending remote set point. So the composition controller is cascaded to the tray temperature controller, and the tray temperature controller is cascaded to the flow controller on the reflux. So we have a flow controller on the reflux. So we measure the reflux flow rate. And so the temperature controller is cascaded to the flow controller on the reflux. In addition, the feed composition is fed forward to the reflux flow controller. Oh, great. This is another thing. So the feed composition, so we measure the feed composition right here. So the feed composition is fed forward to the reflux controller. So what I need is I need a feed forward controller. So the measurement of the composition goes to the feed forward controller. And this is fed forward, so in addition, the feed composition is fed forward to the reflux controller. So this is fed to the reflux controller. So we have two signals that are going to the reflux controller. So again, we can combine these feed forward and feed back as we have previously. All right, so here we have composition cascaded to the tray temperature, which is cascaded to the flow. So if this temperature doesn't change at all, then all of the control comes from the feedback control. If everything is operating at its right set point and we see that the composition of the feed changes, we know that this feed forward is going to have to tell this valve to open or close. One thing though that we may need to do is we may need to add a dynamic compensator. So depending on the time scale for which the change in composition affects the required change in the reflux flow rate, because again, changes are gradual, we could add a dynamic compensator either to the measurement, to the measurement value, or perhaps to the value of the flow controller. Likely, we could put the dynamic compensator on the sensor value, or perhaps it could be a filter value which acts the same way, adds a lag to the measurement. Okay, finally now though, is we have the level controller for the accumulator is cascaded to the flow control of the distillate product. Okay, level controller. So we have a separate controller, level control on the accumulator is cascaded to a flow control on the distillate product. So a flow control on the distillate product, that means we also have to measure it, FT. So the level controller sends the remote set point, which means that the level controller would have a specified value. So on here we have two independent feedback control loops, one to control the level of the accumulator with the distillate flow or product flow, and then we have another controller that controls the composition of the product by changing the reflux valve, and we have a feed forward component that accounts for changes in the composition of the feed. Okay. There are a few other problems like this. It's good to work through these problems. If you have questions, I'm happy to help with some of these. All right, moving on to another example. Here's an example where we're preheating a process fluid. So the process fluid is preheated. It's going to enter a reactor, and the composition and the temperature, so the composition and the temperature coming out of the reactor can be correlated with each other. So we're going to measure the temperature of the product coming out of the reactor as our primary control objective. So this is our main CV, is the temperature coming out of the reactor. Okay, so for this system, this process fluid is being heated, and it's going to go on. So we know that the temperature of the stream coming into the reactor is going to be important. It's going to affect the temperature coming out here. So in feedback only mode of operating based on the system, okay, we have a specified temperature. This controller is going to change the amount of fuel based on the measurement of the temperature coming out. What we know is that the fuel is going to first affect the temperature. So the flow of fuel is first going to affect the temperature of this stream, which is going to affect the performance of the reactor and the temperature coming out. So in order to improve the performance of the system, I want you to design a cascade scheme that accounts for a variety of types of disturbances associated with this process. Okay, so for this example, what we might do is we'll first get rid of this. So to incorporate Cascade, we have our primary control loop who's going to provide a remote set point to an internal loop. Okay, what we want to do is we want to control the temperature of this stream right here. So we can add a temperature controller to measure the temperature of the process fluid that's heated through the system. So we're going to provide a remote set point, so we're going to keep this temperature where we want to be, and the internal controller is going to change the flow of fuel to the system. All right, so this type of cascade process is going to account for any sort of changes in flow rate, temperature, etc. of the process fluid, and also any changes associated with the fuel. They can all be accounted for using this type of system. Because again, the important thing is that the main thing we know that's going to affect, the main variable that's going to affect the temperature of our reactor that can be changed based on this manipulated variable is going to be the temperature of the stream. So this manipulated variable first affects the temperature of the process, temperature entering the reactor, which affects the temperature there. So this was what allows us to do Cascade. Okay, here's another example of a distillation column. Now in this case, we have a condenser. So shown here is a condenser. In this case, we have some of the tubes of the condenser are exposed to vapor and some are exposed to liquid. And so in this case right here, we want to control our control objective for this system is the pressure of the distillation column. So we have a specified value of pressure in the column, and we can change the pressure by changing the level in this system. So in feedback only mode, we could open and close this valve. So again, as we open this valve, it decreases the level. As we close the valve, it'll increase the level, and that's going to affect how much of the vapor condenses. Okay, so in this system, there's a variety of disturbances that can affect the process without this valve changing. So some of those things might be this level could change by something else happening, which would change the pressure of the system. So think about ways of incorporating a cascade or feed-forward or ratio control scheme to account for changes in specific disturbances. Okay, that's something I want you to do on your own and think about, and maybe we'll come back to this one later. Okay, we're looking at the stripping section of a distillation column. In this case, we have the feed to the column is going to be our main disturbance. So we want to incorporate a feed-forward strategy to account for changes in feed flow to the disturbance. So go ahead and do that, pause the video, and then come back. All right, let's see how this works. So our main control objective, again, we want to start with our primary control. We care about the composition, so we have a specified value coming in. So the composition is going to change the valve that controls the flow of steam to the column. Okay, but we know that the steam flow can change, so instead of just doing this, I want to incorporate a cascade loop that accounts for changes in the steam pressure. So I'm going to measure the flow of steam, we're going to open or close a valve, and so now in this case we have our composition controller is going to be cascaded to a flow controller or a pressure controller around the steam. Okay, so if the feed is the main disturbance, we can incorporate a ratio control. So based on the feed to the system, based on the amount of feed to the system, we have to increase the amount of steam. So the feed is going to provide the measurement of the feed is going to be sent to a ratio controller. The composition controller is going to provide a remote set point. Okay, but also one of the things we need to consider though is that the feed to the column is not going to immediately affect the composition. It's going to take some time before the composition affected by this change in feed rate. So we don't want the steam temperature to increase right away. So because of that, we want to add a dynamic compensator to the system. So how do we do that? We could either put that here, we could put it here, we could put it here, a couple places, but there's really only one place where it makes sense. Okay, so this primary control loop is setting the ratio between the measurement of the feed to the system. So the ratio calculation is going directly to the cascaded flow controller. Where we need to put the dynamic compensator is right before the ratio controller. If we put it after the ratio controller, the ratio is going to be calculated and the dynamic compensator is going to interfere with the primary feedback control loop. So this loop right here should be independent of the feed forward stream. So we would measure the flow of the feed. We would add a dynamic compensator, which essentially it slows how the change in the measurement of the feed is sent to the ratio controller. So the ratio controller is going to more slowly change the flow of feed based on the measurement of the feed to the process. All right, so I think that's all we have for today. I hope this was useful. Work on some additional problems, and we'll see you next time.